Okay, so in the last video I introduced forward velocity and we saw how we compute it as the tangent vector to any world line. Now in this video we're going to explore a little bit more the normalization of this forward velocity. We're going to see how we can essentially use the metric to compute the length of the forward velocity vector and how the length of this forward velocity vector, or the Minkowski length rather, is going to effectively completely determine the velocity characteristics of a world line that has that forward velocity. So let's just keep drawing our space-time diagram for reference. Remembering we have our light cone, which is the zero separation from the origin, and then our positive and negative hyperbole. So this is just our space-time diagram, and now we're going to consider any world line, and just for simplicity let's let that world line pass through the origin, and let's look at the forward velocity vector to this world line. So as I defined in the previous video, we had the forward velocity vector. We essentially, we define it as the parameter derivative of this world line. And if you remember, we were expressing our world line as just a vector of functions that kind of specifies each coordinate. So the forward velocity is just the parameter derivative of our world line, and then expressing our world line is just a vector of functions. We saw the parameter derivative is just dt by d tau, and then dx by d tau, and then we saw, well, this dt by d tau defined as being this thing called the Lorentz factor. And then we can rewrite this dx by dt as, we can rewrite the dx by d tau as dx by dt by d tau, which is just the Lorentz factor. And then we said, okay, this dx by dt is just now the coordinate velocity. So this is now just a fairly concise way to express the forward velocity. But you should always remember that this gamma is a derivative of dt by d tau, and this v is a derivative of dx by dt. So let's now start exploring effectively the Minkowski length of this forward velocity. Forward velocity is just a vector in space-time. We can compute the length of that vector using the metric. So if you remember, we had the Minkowski metric, and we can use this now to compute the space-time lengths of vectors by remembering that these are one forms. We can just insert a vector into that one form. So if we insert two copies of our forward velocity vector, we're going to get the length of that forward velocity vector. Now I could go through the full calculation, say express the forward velocity using its basis, and then sub into the one forms and go through and do the whole calculation. But really, because the metric is so simple, we can just skip a lot of those steps, or we could just now realize or remember that what the metric essentially does when it acts on a pair of vectors, just simply expressing their components now, we can write it like this. So we kind of juxtapose the vector components with the metric components. And now if you remember, what this metric does is it contracts, or it lowers one of these vector indices. So it lowers this first index, and then we're simply just left with a one form of vector contraction. And now because our metric is a really simple form. It's just a matrix with -1 and +1. This expression is fairly easy to compute because we can just fairly easily work out what the one form u mu is going to be. We essentially just need to put a minus sign in front of the first component. And so now, rather than subbing in a whole expression with basis vectors and manipulating Kronecker deltas, we can just take a really quick shortcut, remember this expression, and then realize, oh, okay, well, we just need to take the vector components, turn them into one form components by putting a minus sign on the first one, and then we just multiply and sum our components as if we were doing a Euclidean dot product, say. So I'll just write this out. It's going to be, so it's going to just be u0, u0, but now I can remember that I can just write this by putting the minus sign, or if you like, the eta 0, 0 component, and then I just need the eta 1, 1 component, like this. And so essentially, this is just going to give us minus c squared gamma squared plus v squared gamma squared. Okay, so this is now the space-time length, or sometimes you would hear this referred to as a norm, or the Minkowski norm, but it's essentially just the space-time length of our four-velocity vector. So I'll just kind of give it a shorthand norm symbol, just for writing it down briefly. But now what this equation represents is effectively the length of a four-velocity vector when measured from the origin. Okay, so this is a length. It's something that's ds squared. It's proportional to a ds squared. It's going to have the same kind of character that we've realized for our just simple spacelike or simple space-time distances. The length of this vector we're going to also see can be positive, negative, or 0. And we're going to see that the three different cases are going to correspond to three completely different behaviors of particles moving through space-time. So let's start exploring this now. So I'll just rewrite quickly. We have the full velocity, and then we've computed its norm, or its length, which is effectively this expression, and we just saw minus c squared gamma squared plus e squared gamma squared. So this expression is giving us the space-time length of our four-velocity vector. So we're just taking the full velocity, measuring it from its base being at the origin, and then just seeing how long that full velocity vector is. And so now let's start exploring the three different cases which we're going to be expecting. So let's first look at the case where this length, now I'm going to represent this Minkowski norm or contraction just by writing it in a modulus symbol. Let's examine the case when this length is 0. So this expression being 0 just means that this expression is 0, and now essentially we can just simply realize that this is going to be true whenever these two objects are equal, and so gamma squareds are going to disappear, and we're simply going to be left with v squared is equal to c squared. So when the full velocity length is equal to 0, as we saw, this implies that v squared is equal to c squared, or equally we could write that the modulus of v, or the absolute value of c, has to be equal to c, or simply just that v is plus or minus c. So, if the full velocity vector has 0 space-time length, we know that the velocity, or the coordinate velocity, that the world line that full velocity vector is going to correspond to is going to have a coordinate velocity of plus or minus c. So now what we have to realise is that on our space-time diagram, if you remember, we plotted these two straight lines which correspond to all of the points in Minkowski space which have 0 separation from the origin. That now a full velocity vector that also has 0 space-time length is just going to be some vector that effectively points from the origin to any point on these two lines. And now we can just really easily see that a full velocity vector that points along these two lines that are at 45 degrees, essentially we can just kind of intuitively see that this is now going to have to be the line x equals plus or minus ct, because, well, we could have realised this in a number of ways. We could have just taken our interval, set the interval equal to 0, and then just realised that c squared t squared is equal to x squared, or that x is equal to plus or minus ct. But then now here, with this velocity being c, we could just integrate this and find that x is also plus or minus ct. And so what this is now describing is essentially a world line that is essentially just this line, so a world line that is this line that has 0 separation from the origin. A full velocity vector which is tangent to this line is going to be a full velocity vector that has 0 space-time length. And we've now just seen that that vector, a full velocity, is going to produce a coordinate velocity that is always equal to c. Okay, so that's the kind of special case in which our vector has 0 length. We've seen that it always fixes your velocity to be, or your coordinate velocity to be equal to this constant c. Now I don't want to go into any more depth about what c is or what it means yet, just noting the rather interesting feature that full velocity with 0 length always has a coordinate velocity of plus or minus c. Now let's see some similar features. What about considering the case when this full velocity length is less than 0? So if the length is negative, remember we had that space-time separations from the origin to points on this purple parabola had ds squared less than 0. And so we should expect that if a full velocity vector has a length less than 0, from the origin it's going to have to point somewhere onto one of these two parabolas. So now, just already, without even doing any sort of calculations at all, just by simply stating or requiring that this full velocity have a negative space-time length, we can already see effectively all of our vectors, our full velocities, are going to be constrained to lie between these two orange lines that I've drawn at 45 degrees. And so all of the full velocities that have negative length point kind of within now what I'm going to start calling the forward light cone. So if your full velocity has a negative length, you're always pointing somewhere on this forward light cone. Intuitively now, from this picture, we can already just see that the maximum, or the largest kind of value of the full velocity gradient is going to point all the way out here until it eventually reaches this 45-degree angle line. And so somehow, just by having a negative length, we've already constrained our forward velocity vector to lie between, or to lie within, the forward light cone. So let's just see now what this corresponds to. Well, we have that minus c squared gamma squared plus v squared gamma squared has to now be less than 0. So if I just add c squared gamma squared to both sides, I get this, and then the gamma squareds are going to cancel. And so we're left with v squared has to be less than c squared, or v has to be that the magnitude of v has to be less than c. So we've now realised something extremely important, something that we could already kind of see just by looking at this picture, but that essentially if your forward velocity has a negative length, i.e. when measured from the origin, its length is going to have to lie somewhere on one of these negative ds squared hyperbole. Essentially having this, or essentially by constraining this vector to always lie within now the forward light cone, which is effectively what this is doing, we can now see that the space component of the forward velocity, i.e. how much of the component points in the space direction, is effectively constrained to only ever be plus or minus whatever this component is that would give a 45-degree vector. And so essentially, as we saw that this space component corresponds to the coordinate velocity, this is now effectively constraining our coordinate velocity to always be less than this c. So essentially, just now by looking at the space-time length of forward velocity, we've completely constrained the coordinate velocity to be less than c. So we're going to see the significance of this in much more detail in upcoming videos. Okay, so that's for a negative velocity. We've seen that it produces a coordinate velocity that always has to be less than c. And so now, as you can probably guess, just simply for the final case in which the length is positive, I won't go through it, but it's exactly the same calculation. You just find that the magnitude of the velocity has to be always greater than c. So now these three cases are going to very closely resemble our just points in the geometry. You remember we referred to points that have a 0 space-time separation from the origin as being light-like or null separated. So now we refer to effectively the character of this forward velocity by referring to its length. So if the forward velocity has 0 space-time length, we say that it has null character or light-like character. And then likewise for positive and negative, we say that negative lengths corresponding to vectors that point within our forward light cone, we say that these are timelike. This would be a timelike vector. And then for positive lengths, i.e. vectors that point outside of the forward light cone, corresponding to a coordinate velocity that's greater than c, we would say that these are spacelike vectors. And so one thing that we're going to see when we start talking more about kinematics is that the character of a world line is effectively fixed upon creation. You can never go from having a timelike for vector to then that vector suddenly becoming spacelike. Effectively, these are distinct regions or distinct kind of characters in Minkowski space. If you're in the timelike, pointing in the future light cone, the forward light cone, that's always where you're going to be. Your forward velocity can never stray outside of this v less than c condition. So, in summary, we defined the forward velocity in the last video simply just as the parameter derivative of worldlines. And we kind of saw that the two components effectively represent some sort of velocity through time and then a velocity through space. And then we referred to this as the coordinate velocity. And now we've seen, simply just by looking at the length of this forward velocity vector, using the metric, the length of this vector effectively constrains the possible values that this coordinate velocity can have. Now we've seen that if the length is 0, what we would refer to as a null character forward velocity, your coordinate velocity is always fixed to be equal to this constant c. And then if the length is negative, your coordinate velocity is always fixed to be less than c. And then likewise for positive, your velocity always has to be greater than c. So now just giving our interpretation of this diagram using this light cone, essentially all of the vectors which lie within this 45-degree forward light cone, they represent physical or the velocities of real particles, and now velocities that point outside of this forward light cone, i.e. that correspond to having a coordinate velocity that's greater than this constant c, we're going to see they would correspond to unphysical particles, because essentially what we're going to realise is that if you're a real particle, your world line is always timelike, and you can never have a coordinate velocity that exceeds c.